This lecture and the next one are going to be the most crucial and important in the whole series. They're a pair, they've got to go together. So you won't completely understand why we're doing this one until you see the next one as well. And then you'll see the reason why we've emphasised the protocols that we need. This lecture will show why we need those protocols we did in the first lecture. Here we want to show for the first time, show, not state but show, sorry, that's not the right one, that's the one. Yeah, to show that this is a real subject. And the next step is going to be deeply mathematical, though you won't realise it's mathematical until the next lecture. You won't realise the mathematical nature of this lecture until you see the second one in the series. It's obviously not going to be conventional mathematical physics because we need complexity for that, and this is not complexity, but it will certainly lead to it. Now, we've done a methodology in a mathematical toolkit, and what we're going to do is try to get this embryonic level of physics, get that out. And if we do that, then I don't think we can ever look at physics the same way again. We must always bear this in mind once we've done it. It isn't an exercise in philosophy, it's a completely physical discussion, but it's at the most primitive level at which you can say this is actually the lowest physics level. And I'm going to say that we can begin to answer certain questions that we can't hope to answer at a more complex level. It's going to be very inductive, and we've got to organise all our information in an inductive way. And what we need is to use the very principles that we've been talking about and the pre-prepared mathematics. We've got to cut through a lot of layers of complication to find what we think might be more primitive level. This is really talking about removing the complexity and getting to the more basic level. And big simple ideas, why time flows only one way and that kind of thing, need the sort of answers that we hope to look at in this sort of area. And we need to develop an aptitude for the recurring patterns, which I've already mentioned. This isn't pure speculation. There's no constraint on what we can think, but there's certainly constraint from physics on what we can accept. Because immediately we get these foundational ideas, we need to find out the consequences, and if they go wrong, then the ideas are wrong. It's as simple as that. They go wrong very quickly because if you're at a more foundational level, clearly everything that's based on them will go wrong if they're wrong. Whereas broadly correct ones might produce a few issues, but we will begin to see that they're beginning to work in the right direction. You can't bury faults in the details here because there aren't any details. There's no model-dependent part. You can't say, oh well, if it was that value or that value, it'd be all right. You can't do that here. It either works or it doesn't to a large extent. So, we said that the most primitive ideas are those that survive when we descend lower and lower in scale. And they include space and time, something representing matter in its point-like state, and something representing energy over connection between the points of matter. It could be that there are other ideas, but we have to start somewhere, and if we start with these, we'll see how far we get. So the last two, in some sense, clearly represent the sources of foreknown physical interactions. And if we think about fundamental physics, it seems that if we really think about physics, there's not a great deal other than space and time and the sources of interactions. There's not a lot else. I'm going to look at a concept I am going to call charge. And it does include the concept of charge as we know, it's electric charge, but it includes other ideas. It includes the type of charge we talk about when we talk about charge conjugation. When we talk about charge conjugation in particle physics, we mean more than electric charge. We mean the whole structure of the particle as a particle in many ways. So it's not as simple as we think. Weak and strong interactions require a similar concept, which is incorporated into charge conjugation. And we've already partially unified the electric and weak forces, and so that does suggest there's some sort of similar structure at the basis of those two forces. We also believe that there's probably a bigger unification at a higher scale. And so I am going to consider this concept as a kind of single parameter with three components representing these three interactions. If this turns out to be wrong, then we'll find out quickly. Something seems to break the symmetry between them. Yes, we believe that there is some particular energy regime, which would be a grand unification, in which all these forces, three forces, would be alike. And we know also from quantum field theory that the three forces do have a common component, a common U1 component, a Coulomb component. Each of the forces has a Coulomb. Perhaps we need a conjecture here based on the idea that we may have seen the pattern before. Now, our mathematical discussion last lecture showed how we could package two three-dimensional structures and get a broken symmetry. Maybe that's what's at the back of this. Maybe we can guess that's going to be the reason why we break the symmetry. We'll find out if it is. And so we will make that provisional assumption that that's going to happen. If it's correct, then we will very soon find out that we've got the right structure. If it's incorrect, then we'll equally soon find out that it's wrong. Now the other concept, this is gravity now, the other concept is the energy concept, the mass energy concept. It's difficult to get away from that, and we also know that it's the source of the gravitational interaction, and that it's some way differentiated from the other three. It's not the same as the other three. So we can call it energy or mass. Now the reason why I call it mass is because I like monosyllables. The primitive concepts are like monosyllables. So if I had to say energy, that would ruin that nice symmetry between these four parameters. We also want to emphasize its role in gravity. And I want also to show how the concept of energy in the quantum sense and its relation to mass as the gravitational source are emergent properties. So there is a concept of energy which is an emergent property. Even though mass and energy are related, there is a concept of energy which I wish to show is emergent. So that's why I call it mass. Now there's no physical system in which the rest mass can actually be separated from a dynamic component. There's no such thing as a particle at rest. No such thing. Because all particles are dynamic. You can't observe them unless they are. And also, even the rest mass itself is part of a dynamic process. That's quite subtle, but there's a subtle dynamic process involved with the rest mass of fundamental particles, which we call Zitterbewegung. We could have identified these concepts by the old method of dimensional analysis. And the reason why dimensional analysis is so effective is because they do have a kind of foundational feel about them. They also feature at a fundamental level in things like the CPT theorem. Three of them do. Charge conjugation, which is all the charges, parity, which is space, time reversal, which is time. The only one that's absent is mass, because you can't reverse that one. If you could reverse mass, it wouldn't be a CPT theorem, it would be an MCPT theorem. And that's one of the most fundamental theorems in physics. It's really at a profound level. I also want to show, and I will show this more definitely later, that they're purely abstract. None is actually any more real than any other. People think of charges, and masses and so on as being sort of tangible. You can actually see them as substance in some way. But that's purely abstract. It's just as abstract as space and time. It's no more real than they are. They're all in fact manifestations of pure algebra, and I want to show that by the end of the next lecture. We're not going to assume that the most fundamental imaginable concepts, but the most fundamental imaginable that can be described as purely physical. In the very last lecture, I will actually go to a stage beyond those to show that they are not the most fundamental concepts. So I'm not assuming that at all. And remember, I have this concept of zero totality, that nature isn't characterized by anything like this, and we've got to find out how that works in this structure. So the most primitive abstract concepts have to be more fundamental than either the laws of physics or the structure of matter. You can't do these without more primitive concepts. Now, interestingly, only one of these concepts can actually be measured, and that's space. You can't measure time, or mass, or charge, even though we think we can. Even though measurement is the only means we have of investigating nature at all, we can only measure one of them. So it's interesting why we use more than one concept. All the ingenious devices we've ever used for measuring and recording data, however sophisticated, are essentially nothing more than a pointer moving across a scale. That's all you can ever do in physics. It may be done for you, it may be done without you seeing it, but that's what it's doing. And you can't do anything other than that. However, for some reason, we're channeling it through another 3 conceptual structures at least, as though they were equally valid with the one that we can measure. And of course, the entertainment industry wouldn't exist if this wasn't true, because space is used to substitute for people being there. That's what sound is. Sound and colour is really spatial variation. All the things that we associate with other things, holograms, so on, the sort of make-believe is all based on the fact that space is the only thing we can measure and observe. And we infer everything else, including the passing of time and including the behaviour of matter and all that, as a result of observations of space or some space type thing. Another aspect of space is that it's actually universal. Every single thing we do is a measurement of space. I've got a device here which measures space, a ruler, but that device could equally measure space or anything else. Any object at all is a measurement of space. It creates a standard for measurement of space. So it's universal. Everything we do is a measurement of space. Happens at all times, all places. And though we can sense time passing, the second law of thermodynamics tells us which way time is going, and we can detect whether we're going in the right direction or not, we can never actually measure it. What we're doing when we say we're measuring time is measuring repetitions of a spatial interval. Some of the early clocks were based on the idea of isochronous devices, ones that had a repeated pattern of spatial motion. For example, a balance spring in a watch or a pendulum in a clock. All the motions of the planets in the universe. Simple harmonic motion is a classic way of measuring space, measuring in inverted commas. Even relatively modern devices like atomic and digital clocks do internal oscillations which are counted internally. So in all these devices, the space is measured, not the time. We simply infer the time. We also need special conditions. We can't measure time without acceleration and force. We don't need those in principle to measure space. But even sending a light signal, if you measure time using a light signal, you've still got to have a reflection to be able to measure it. So in effect, you've got acceleration and force always when you measure time. And these are second order in time. Acceleration and force are second order in time. They're the second differential, the rate of change of the rate of change. So they're further removed from a direct time measurement. The same is true of measurements of mass and charge, which are only, again, possible when we measure a force. And again require a pointer moving over a scale. Now, this special nature of space has long been of interest to physicists and philosophers. And several people have tried to reduce the whole of nature to space in some way or other. Descartes is famous for saying all is extension. Einstein's program was eventually to bring time into space, then mass into space, and hopefully charge into space, with Kaluza-Klein adding the fifth dimension for electromagnetism. And in a sense, the string theory is trying to do the same thing in a sense with the other forces. So there is a sort of feeling that space is special and that somehow we could actually make everything part of space. There are problems even with the unifications we've achieved. We have a unification of space and time in special relativity, a unification with mass again in general relativity, but we're not actually saying that the time is actually space. It is actually different. We're combining it, but it's not the same thing. We still have time and we still have space. It isn't just one concept. There are a structure that combines two things, but they're not the same thing. They're different. And quantum mechanics tells us that they're different. It tells us that one space is an observable time, the other one isn't. They're quite different in quantum mechanics. So there is a problem even with the unifications. There's not a problem that we should do the unification, but there's a problem if we think it's foundational. That's the problem. And even if we could get a multidimensional space-like structure, we wouldn't have a theory in which nothing was arbitrary. You'd say, well, where does this come from? Why have we got so many dimensions of this? Why have we got 3 of that and 1 of that? why we got 9 of this and 1 of that. It still doesn't explain anything. It is possible that that may happen at a higher level, but it's not what we are trying to explain here. So, if we had a multidimensional space-time as the foundation for physics, then we wouldn't have anything foundational to explain where that came from. And we can't have that. We can't have anything arbitrary. It's too arbitrary. And as I say, quantum mechanics tells us that it's not a complete union, that there's something disunified still about it. So this appears to be an emergent union at the first stage of complexity, not a foundational one. Now, if we can't reduce all the concepts to space, perhaps we can find relationships between space and the other concepts. If we can't establish identity, perhaps we can find symmetries. And the symmetry that is most fundamental to us is the one of duality. Because duality allows us to get our zero totality. If we have two things that are like plus and minus 1, and effectively a cancellation in total. So we can guess that the symmetry that we're looking for here, in this part of the proceedings, is the C2 group, the most basic group, the one that includes 1 and minus 1 as an example. Now, if we had perfect duality, there would be some characteristics in which two concepts are identical and others in which they were opposite. And we might not actually know that dual concepts weren't identical. We might only see those parts of the concepts which are identical, and not the parts which are opposite. Perhaps that's what we're doing when we look at a combination of space and time. Okay, we're now going to explore 3 fundamental dualities. Now, when we've done this, in the next lecture we will see how this leads to the mathematical structure we're looking for. The first duality is between conserved and non-conserved quantities. And I'm going to say that duality pairs mass and charge against space and time. If you had to choose physics laws that you were going to bet on, which would still be around in 500 years' time, my first guess would be the conservation laws. They're among the most solid in physics. The ones that we're most likely to believe, the ones that we would, if we get an experimental result which appears to violate them, we would say the experiment was wrong. Right, so physical systems say one quantity is conserved or several quantities are conserved while others aren't. That's how we build our equations. Most of our equations are saying something of that kind. So conservation laws are very specific. So this is where our friend Oliver Lodge made a contribution here. Conservation laws are very specific. Mass and charge aren't just globally, just all over the universe, but they're locally conserved at each time and place. Each elementary charge and each element of mass has, Oliver Lodge said it about mass, energy and identity. He called it the identity of energy. So the identity is that sort of thing that goes with it forever. It doesn't lose it. So your element of energy retains its identity whatever transformations it goes through. It's like a person. It has an identity. A unique label, if you like, and it carries with it all the time. And this is what we also call local conservation. There's also a property called non-conservation, and we might think, oh, just means it's not conserved, but it doesn't. It means it's dual to conservation. It is the exact opposite in every respect from conservation, and we can examine that and show why. If conserved quantities have identity, then non-conserved quantities, their elements have no identity. Space and time have no identity. So we can't single out a unit of space and time. We can single out units of mass and charge, but we can't single out units of space and time. And there are 3 fundamental symmetries which express this perfectly. The translation symmetry of time. One moment in time is as good as any other. Translation symmetry of space, one position in space is as good as any other. The rotation symmetry of one direction in space is as good as any other. They have no fundamental identity. Conserved quantities are translation and rotation asymmetric. It's exactly opposite. Each unit is unique. You can't replace one by another. Mass and charge have identities. So, let's call it the translation asymmetry of mass. We can't replace one mass element with any other. We can't replace one charge element with any other. This one is very interesting. Rotation asymmetry of charge. That means that we can't replace one direction. Now, if we had a three-component charge, we can imagine it as three sort of axes, electric, strong and weak. And what we're saying is we can't rotate one into the other. So
Which is completely conserved.
Completely conserved. We can't rotate one into another. And we have, in fact, laws that say that. We have baryon and lepton conservation, which depend on the fact that we can't rotate these things. Because baryons are the only particles with a strong charge. Unless they can transform into something else with a strong charge, then we can't get rid of them. And this is a very important thing. This is why I say you can never, ever, ever, and I'm going to stake everything on it, have this concept of proton decay, as is claimed. You cannot decay a proton into a positron and a neutral pion, because a positron and a neutral pion do not have a strong charge. So you cannot decay the proton into it.
Proton decay requires a quark to change into a lepton.
Yeah.
You say that's
Absolutely forbidden. Absolutely forbidden. You can never do it because of this fundamental property. And I've been saying that for a very long time. Long before, when people were saying the proton would decay, I said it wouldn't.
Still could.
Still could, but it hasn't. But I'm saying it won't. So I'm staking everything on saying it won't.
So for as long as you live, we...
And now another key property of non-conserved quantities is gauge invariance. I don't want to go into detail about this because it's quite a complicated idea. Well, it's simple really, but it's rather abstract. But it's the thing that tells us that we can't have an absolute potential for something. So we can't have an absolute potential for something. Our field terms will be unchanged if we change the potential. And the reason why we're changing the potential is because the translations and rotations of symmetry in the space and time coordinates don't affect the charge conservation. So the charge is conserved, but the mass is conserved, but the space and time is not. And that's why we can have any potential we want. So we can change the coordinates as much as we want, as long as the conserved quantities remain the same. And also, gauge invariance is local, exactly like the conservation laws. So non-conservation is local, just like conservation. That's what gauge invariance is, local. So gauge invariance, so these are not passive constraints, by the way. We actually forced to write down physical equations which incorporate them directly. We say these are fundamentally part of these physical equations. We can't write a physical equation unless we spell it out that these are true. That we have gauge invariance and we have translation and rotation symmetry. We have to have this non-conservation built into our equations. This is why we structure physics in terms of differential equations. The things that differentiate are the variables, space and time, not mass and charge, and others derived from them. In principle, are differential equations. The fundamental things that have to be differentiated are space and time. And I say that it's because of the variability intrinsic of space and time that we have the path integral approach in quantum mechanics. So we have to some overall possible path. None can be preferred. We can't say this is what the real space is. And I say this relates to the concept of the interchangeability of the particles. And then why should we worry about God playing dice in the quantum state? God does play dice in the quantum state. Because if we define space and time as non-conserved quantities, this means they should be subject to absolute variation as long as we preserve conservation laws. So if we've got an electron, free electron, it can be anywhere. There's no way of saying where it is. If we bring it up near a proton, then we introduce a conservation law, conservation of angular momentum, conservation of energy. So we've got conservation law, and then the electron can be anywhere it wants to be as long as it obeys that conservation law. So it doesn't have any fixed position, we just restrict the variation it can do. And then we bring up another hydrogen atom and make it into a molecule, and then we change our conservation principle to a new one, a new conservation structure. And the electron can be anywhere it wants to be within that structure as long as the conservation law is preserved. So we don't have any problem with that. When the interactions are on a massive scale, we can actually do a measurement and almost pin it down. It isn't the measurement itself that makes the situation classical. It's just the variations are restricted by more and more conservation laws. And this is what we mean by, effectively, by doing a measurement to collapse the wave function. But I'll say more about that a lot later. Now, let's mention Noether's theorem, because we've already talked about these three invariance principles here. It's well established that those principles also have completely linked conservation principles, so you can swap one for the other. So the translation, symmetry of time, and the conservation of energy are the same principle. So we got three such principles. So rotation, symmetry, space, conservation of angular momentum. Now I'd say Noether's theorem is a natural consequence of defining these properties to be symmetrical and dual. Because all the time you've got a non-conservation principle and a conservation principle. So you've got this duality between the two. Perfect duality. And we can actually make a couple of guesses here. And if we're right, then that will be interesting. And if we're wrong, that will show that we're on the wrong lines. Because by pure symmetry, we can guess at least one extraordinary result. And I won't be able to show why that's true until the next lecture. But this is quite a remarkable result. If we can extend not Noether's theorem, but the illustrations of Noether's theorem, we can say these two red ones here are extensions of interpretations of Noether's theorem. And as Rodi was talking about earlier, energy and mass being the same thing. So the conservation of energy, conservation of mass are the same thing. So translation, time translation, and mass conservation are the same thing in this way of thinking. Now I'm saying that conservation of momentum, therefore, by a symmetry that one can do on a far more fundamental level, is the same thing as the magnitude of charge. Now that's not very different from gauge invariance that we were talking about. That's effectively that sort of thing. Momentum, space translation, and the magnitude of charge are basically the same thing as gauge invariance, local gauge invariance. But this one here, angular momentum and type of charge, so those three things are the same. So in other words, that law I was saying about conservation of baryon and lepton number, you can't rotate the axes of the charges, you can't do that. That is the same as conservation of angular momentum. Now that is a bizarre result. Now if we can prove that true, then we will be a long way to justifying this, because to get such an extraordinary result and find a reason for it within the system will be very interesting.
So let me be clear. At the moment you're saying these are your conjectures,
yes,
which you're then going to prove.
Yes,
okay.
At the end of the next lecture.
Yeah,
I won't prove it. This one here is a version of gauge invariance, but this one here I'm going to do at the end of the next lecture.
Using the mathematics, yeah.
Yeah, I will actually show that to be true. And I couldn't work out why it was true for at least 20 years. I knew it was true, but I didn't know why. But eventually I did. So we've not got any good reason for doing that, but we'll find out why in the next lecture. And it's an extraordinary result. So if you can make a prediction as bizarre as that, remember what I'm saying here, conservation of angular momentum and the conservation of the type of charge, the fact that you can't rotate one into another, are the same law. I'm saying that. It's a bizarre result, and if it's true, then that will be very interesting. Now the next one is the real and imaginary distinction, the norm 1, norm minus 1. Now, effectively this, I will show, is just an algebraic property. This is just an algebraic property, obviously, but so is this. But I won't show that yet, next lecture. Now I'm going to pair them in a different way for this. Well, relativity already uses imaginary charge. space and time in a 4 vector with 3 real parts and 1 imaginary. So you've got Pythagoras' theorem in 4 dimensions with minus c squared t squared. So the simplest way of doing that is to do it as a 4 vector with ICT, not CT. And again, with energy it's the same, it's also 4 vector. We will use this more than we'll use the space-time relation, so that's why I've introduced that. So we may well ask, why is the time or energy component imaginary when we do it mathematically? It's just purely mathematical. It's not saying this is an imaginary quantity, it doesn't exist or anything. It's saying it's mathematically norm minus 1. So why do they have different norms? Well, you could say, a physical argument would say that light is retarded, which it is, of course, but we have to remember this is the foundational level and we've not got any light or relativity yet. So sometimes people say that the Minkowski space-time is just a trick, mathematical trick. But one has to ask, why do mathematical tricks work unless they represent something which they should represent? So they don't just work because they work because of some other reason. In any case, vectors in our representation, we've discussed where we get vectors from, which is by complexifying quaternions. And quaternions have 3 imaginary parts and 1 real. And if you complexify that, you get 3 real parts and 1 imaginary. So in our presentation of vectors, there ought to be a 4th component anyway, which is imaginary. And so that's another good reason. But there's also a physical explanation. We've already discussed this. Quantities containing time to the first power have no real significance or physical meaning, like uniform velocity. This only comes when we've got time squared acceleration and force. Time measurement actually requires, as we've already said, acceleration and force, even if we use light itself. This is totally consistent with what we'd expect from an imaginary quantity, but there's yet another reason. Imaginary quantities are intrinsically dual. Any equation with imaginary quantities in always has a dual solutions, plus and minus. And you can't distinguish between them. You can't say that's the solution and that one isn't. Not so real quantities. You can always distinguish between real plus and minus. You can't distinguish between imaginary plus and minus. You've got to have dual solutions. It's a fundamental part of the operation. So if we use imaginary numbers, we're automatically accepting that duality. Now we know that time flows only one way, which we detect from increased entropy. But physical equations always have 2 directions of time symmetry. So even if we can't reverse time, we can extract physical meaning by reversing the equation, the time in the equation, as with CP violation in particle physics. This is what we call the reversibility paradox. But I say there isn't any paradox if time really is imaginary and the one-way time comes from a different aspect of the quantity. We'll show that it does. We also have a parallel case in relativistic quantum mechanics where we have 4 solutions to the Dirac equation, 2 positive energy, 2 negative energy, 2 positive time, 2 negative time. Even though there's only one side of physical energy. We know that energy is always positive, like time. So if our methodology is correct, if we're on the right lines, if we're always looking for the extreme symmetries and so on, then we should find the same distinction between mass and charge. Of course, we've got to remember that our charge is complicated because there's a broken symmetry involved. The interactions are all different, but we hope to show later where that broken symmetry arises. So let's suppose for a moment that we've got an unbroken symmetry. And that the breaking is an effect of emergence or complexity, as we have seen from our last lecture that it could be. Now, this would be quite consistent with current thinking because it's widely believed that there's an energy regime at which all those 3 interactions lose their distinguishing characteristics and become alike. Personally, I have a particular idea of what they would look like, and I think they would all look like simply a Coulomb law. We would lose all the special characteristics of the strong and weak interactions in such a regime. It's possible that these could shrink and we could be just investigating Coulombic forces. Suppose that we are, because we've got to start somewhere. Now, if we look at the inverse square of Coulomb force, we know that it's really what you get from a charge point source in three-dimensional space. There's a long history of discussing why we have inverse square law forces, and it comes from a point source. It can be shown that, as it were. In non-interactions, it relates to the coupling constant. I don't think the charge and the coupling constant are the same thing. The coupling constant is a measure of the energy associated with the charge. But the charge is a yes or no thing, it's either there or it isn't. But it's related to the coupling constant, and the Coulomb interaction the Coulomb part of any force seems to give it its coupling constant. In quantum terms, of course, it's the probability of emitting or absorbing the relevant boson. Okay, let's look at two very simple laws. Basically this is the Newton law of gravitation, negative there because it's attractive force, and the force vector is coming back towards the source. This is the Coulomb electrostatic law, and you see it's a positive force because it's repulsive. Let's suppose M1 and M2 are identical and E1 and E2 are identical. So it's a attractive, repulsive. Why is that? Let's suppose we do that. Let's suppose we make the charges imaginary, and we get exactly the same structure of law as that one. So we can guess that identical charges repel because they're imaginary.
So, Pete, I probably missed something, but didn't you say that mass was imaginary?
Well, I'll explain that. We'll come to that. That will be dealt with. The three charges, electric, strong and weak, are they alike in big? Yes, they are. Yes, we know that, that's true. So we've got of course we've got three-dimensional imaginary quantity, that's our quaternions. Let's have a quaternion with those three. So we've got a quaternion, and a quaternion needs a fourth term. Why not put the mass term as the fourth term?
And the S, E and W is just a scalar.
Yeah, that's just identifying which they are. Now they look the same at the moment, but we can show why they break. So we can propose that charge and mass is 3 imaginary plus 1 real part of a quaternion, whereas we got the 3 real and 1 imaginary part of a 4 vector. So we got a nice symmetry between those. Maybe this is what the quaternions really are about. Maybe they're really about charges, not about space. So maybe this is the real vindication of Hamilton's quaternions. And the direct role in nature. They're also progenitors of space and time, but they're also represent something else. And in fact, if the quaternion representation is logically prior, then the character of space-time would be predetermined by the necessity of symmetry with the charged mass. And therefore, its structure will be determined by the quaternionic form, and therefore lead to spin. So we would have the truly extended form, as I said before. Now this depends on choosing charge with imaginary quantity rather than mass. Why, as you say, why can't we make mass the imaginary? So let's go back to our property of imaginary numbers, plus and minus. In fact, mass is never minus. It's never 2 signs, it's only ever 1 sign. Mass is always a single sign. Therefore, it cannot be an imaginary number. It has to be a dual pair if it's an imaginary number. So mass can't be the imaginary part. However, charge, we've got plus and minus versions because that's what antimatter is all about. And of all the charges. That's what charge conjugation means. We swap the charges up to the opposite sign. We take their dual. For every charge, there has to be charges with the opposite sign. Neutrons with no electric charge have antiparticles because the neutrons still have strong and weak charges. The only type of particle that doesn't have an antiparticle is like the boson, which doesn't have any charges. The masses, as far as we know, as we hope the alpha experiment will show, are the same as for matter and antimatter. We think the masses will be the same. But there's yet another reason for imaginary time and real for these. Now we can observe space directly, whereas time we can only observe the squares. Okay, we got that. We've already done that. Now there's another reason. We observe space directly but through its squared value, and also through its squared value. We've got 2 choices for space. We can measure it as squared value in Pythagoras theorem or directly. Time we can only measure through its squared value. Only measure through its squared value. We can apprehend mass physically in two different ways. We can have force equals mass times acceleration, inertia, or we can have gravity. So we can have direct or squares. A charge, we can only have squares. We can't measure a charge unless there's another charge, or something equivalent, field, which is a charge, ultimately. So we can never measure one charge, we can only measure squared charges. We can measure one mass because we can measure the inertia. We've got two ways of measuring it, because it's a real quantity. Charge is an imaginary quantity, we've only got one way of measuring it. There's a final, and this is also clearly algebraic, commutative and anti-commutative. Again, we're going to shuffle the parameters around again. Space, charge, mass and time. Different pairing. There's in fact a third duality. Mass and time are scalar and pseudo-scalar, real and imaginary scalars. So these are commutative. In other words, that they don't have any components, vector components. Quaternionic charge must be anti-commutative as well. So anti-commutative requires a property. If it's quaternionic, then it's necessarily anti-commutative. So anti-commutative requires a quantity to be both dimensional, specifically three-dimensional, as we've discussed before. The reverse argument's true. Whereas we don't really talk about dimensions. You can talk about one dimension, but it doesn't split into dimensions, the others. Now this is a very difficult concept that I'm going to mention, more difficult than any of the others. In addition to dimensionality, another significant consequence is discreteness or discontinuity. Anti-commutative systems, in my view, are the only source of discreteness in the universe. I can explain that in the last lecture, but I can't explain it today. So I'm going to postulate that anti-commutative or dimensional quantities are discrete or divisible. Well, no, I can show that they are. Three-dimensional quantities are the only discrete ones. That's what I'm going to argue. Now, continuous quantities can't be dimensional. They can't have more than one dimension. Because if they did, they'd have to have some crossover. If you've got dimensional quantities, there's got to be some point, there's got to be some meaning to crossing over from that dimension to the other. There's got to be some zero origin. A one-dimensional quantity can't be measured because scaling requires crossover points. You try and work out any method of scaling without any crossover points. Look at the ruler. We have to have another dimension to see it. Even though we often claim a point in space has 0 dimensions and so on, an area 2 dimensions, you can't generate structure with a single dimension. You couldn't even imagine drawing it. You can draw a line, but it's a 2-dimensional object. A line is representing one dimension, but it's a 2-dimensional object. So, is there a counter-argument that space is a three-dimensional? Yes, there is a counter-argument. If space weren't discrete, we couldn't observe it. Now, by discrete, I don't mean it's chopped up into bits in the way that charge is. Charge is clearly discrete in the sense that you've got that one, that one, that one, that one. Now, space isn't like that. There's a reason for that. I want to say that this is why I wanted to emphasize the fact that there were two definitions of real numbers. Because we have to have a real number system which can explain what space is. Space certainly is defined by real numbers, but space is not like charge at all. It's often represented by a real number line which gives the appearance of being continuous. And the reason why that is because space is a non-conserved quantity. You cannot actually fix its units. So it can be defined and redefined and split up again and again. It's infinitely divisible. That's what its discreteness means. It's infinitely divisible. And that is not the same as continuous. In mathematics, that is the opposite of being continuous. And space has all the characteristics we need for non-standard arithmetic and non-Archimedean geometry. That's what its characteristics are. So there's a very deep distinction between space and time. Time can't be split up into dimensions. And this allows us to finish off the reversibility paradox, which we couldn't finish off before. If it's non-dimensional and continuous, time is irreversible. You can't reverse something that's continuous, because you've got to stop if you're going to reverse it. So time would be irreversible if it's continuous. And it can never be observed, which is what quantum mechanics tells us. This is why we treat time as the independent variable. That's why we do dx over dt and not dt over dx. Because we can't do anything about time, whereas space is open to our adjustments and manipulations. So space is infinitely divisible, and time is absolutely continuous. They're mathematically opposite. If you discuss it with mathematicians, you will see that these are opposite properties. They're as different as they could be. But a fundamental duality in nature allows us to swap one for the other, because we can do that when we package them together. I can't discuss that till we do packaging. So clocks don't measure time, as we've said, but a space. They often need the fact that space is more than one dimension, whereas time doesn't have. So if you've got a thing that swings like that, it needs two dimensions to do it in. Or we need some sort of extra rotational thing to measure it. Zeno's paradox is the famous one. You've got Achilles and the tortoise. Achilles gives the tortoise 100 metres start and can run 10 times faster. So Achilles runs the 100 metres while the tortoise runs 10, then Achilles runs 10 metres while the tortoise runs 1, and so on. So that Achilles never catches up with the tortoise. Well, we know, of course, Achilles does catch up with the tortoise, but that means there's something wrong with our way we're looking at it. And this is what, these are words of by several philosophers and science writers. We conclude that the idea of the infinite divisible of time must be rejected. Remember, it's space that's infinitely divisible, not time, or that it's a logical fiction. Motion is impossible if time is divisible ad infinitum.
But there is then correlatively space.
No, I think he's wrong. I think he's wrong, but he's right about time.
All right.
Yeah, that's what a lot of people have done, so they've never really solved it. Okay. Now, one of the usual strategies is to say we use calculus. But it's interesting that there's only one type of calculus gives us the answer, and that's the type using limits. If we use the infinitesimal calculus, we can't solve Zeno's paradox. So I say they're based on differential with respect to two different quantities, space and time. Because we've got two variables, we've got two methods of differentiation. And in fact, it's nothing to do with that distinction, it's to do with that one.
Read that again, sorry.
It's nothing to do with continuity and discontinuity in calculus, unlike what many people say. It's to do with variability and conservation. But by the way, continuous discrete doesn't mean it's fixed discreteness. In space, it's variable discreteness. So we can never actually fix it. It doesn't come in blocks, it doesn't come in quanta. Space doesn't come in quanta. It's not fixed discreteness, it's variable discreteness. If we differentiate with quant space, we end up with infinitesimals and non-standard. If we do time, we get standard analysis. Now, I didn't know about standard analysis for years. And I knew that there had to be a mathematics which explained this. And when I found standard analysis, I knew that was the mathematics I needed. So I think this is a classic example of the unreasonable effectiveness of physics in mathematics, which people like Michael Berry talk about, as opposed to the reverse idea. I think the same duality applies in physics, but I'm not going to go into detail on this, but I think ultimately you will find the wave-particle duality descends from that distinction. When you put space and time together in a 4-vector format, you can do it mathematically, but you can't do it physically. So you've got to go to the nearest physical equivalent, make it all time-like or all space-like. Whichever you do, it will be not quite completely right. So Heisenberg goes for the particle-like, Schrödinger gives us the wave-like, and both introduce the opposite. Heisenberg's discrete, Schrödinger's continuous, but Heisenberg introduces continuity with the uncertainty principle. Schrödinger introduces discreteness with the collapse of the wave function. So we've got just one more issue. Where does mass stand? This is a very, very important question, which will lead us on to things later. And I say there can only be one answer. If you've got symmetry, all the intrinsic non-dimensionality, it's got to be completely continuous. And in fact, there's no mass which is fully discrete. As I mentioned earlier, all masses are related to the background. All the background is full of mass energy of some sort. Higgs field at every point in space, 0-point energy if you like, lots of different types of energy, ordinary fields even, they're continuous, they're there. There's no empty space, there's always mass in it. Mass is continuous in some form. I say it's possible that the discrete and continuous options could be ultimate response for local and global. And your transition from global to local gauge invariance is the really important point in the Higgs mechanism. The continuous field leads to the generation of discrete mass. And I say that it's the continuity of mass, which is the reason why it's only got one sign. It's just like you can't reverse time because it's continuous, so you can't change the space from plus to minus, because if you could, you go through a 0 point and it's not continuous anymore. So we got three dualities. And I said these are astonishingly exact, and I've looked over these dualities many times and worked at them for a long time, and I can't find any exception. These lead us to new results. These lead us to spectacularly interesting results that we wouldn't have got otherwise. If they represent a truly primitive level, then we might expect dualities of this kind, because that gives us a zero totality. It's none of these things in principle. You can't describe it as any of those things. And in fact, just from simple thinking, you can't actually describe something as being discrete unless you've got something continuous to compare it with, and vice versa. I've heard people talk about continuity as illusion, but in fact, everything's an illusion at this level. It's all abstract. I'll not bother with that. That's basically. Yeah, thank you.
But one electron is as good as any other. And I can show that
Yes.
in scattering experiments, for example.
One electron is
somewhat confused with the.
Yes, well, I agree with you. One
identity
electron
quantum.
is as good as any other, and that is the space and time part of the electron, the wave function. The wave function is the space and time part of the electron, and that's as good as any other, because of this reason. Not the charge, the wave function. That's what's as good as any other in quantum mechanics, the psi 1 and psi 2 and so forth.
We'll
The
wait for
interchange.
that to make more sense throughout the lectures, but
Yeah, that will become more apparent later. It's not the charge that's as good as any other, it's the wave function. And so I agree with that, but it's not what you might think at first.
I'm sorry, just to pick up. I mean, if in this regime of unbroken symmetry, what's to stop them changing one into the other then? I mean, you have your
So
absolute
I don't think,
conservation.
because I think it's an unattainable limit. I think we can work out the energy, but I think it's like absolute zero, it's an unattainable limit.
So,
I think it will be an unattainable limit, because I think it happens at the Planck mass. But let's not talk about that yet, because I'm going to show that we can break the symmetry with the algebra structure we have.
sorry. I wasn't entirely clear about that point earlier, but if you're now basing something on it,
No,
I think
that's
I
a
must ask
different
you
point. Different point.
push your point. We need to understand this.
To understand this, why time has to enter only in the second order
Well, it does.
to make sense.
I know, I'm not.
Velocity makes sense. I get a speeding ticket.
It makes sense. Yeah, but you can't. All things that happen, all changes in nature are due to forces, not due to velocities. All real changes in nature, real events are due to forces.
The absolute velocity.
You're saying that velocity is always relative,
Yeah.
Yes.
but acceleration is
Yeah.
absolute.
Yeah.
That's what you're
That's what I'm
saying.
saying.
Yes. That's what I thought you meant.
Yeah, it is effectively what I mean, yes. It's relativity in effect
Yeah.
that I'm really arguing about.
Something coming at uniform velocity, you don't know what frame it's in. Isn't that?
Can we? I'll talk to you afterwards about it if you want.
I'll belabor that one later.
Yeah,
You're going way beyond my knowledge of mathematics.
that's because I did it last lecture.
Yeah. No, well, even in the last lecture, I mean, when you talk about non-standard arithmetic,
I had to.
I mean, I then don't understand what you mean by continuous.
It's not continuous. A line isn't continuous. It's discrete, but you can actually divide it endlessly because it's discrete.
So can you give me an example of something that's continuous?
Yeah, time.
And why? And you're saying you can't
No, you can't divide
up in the
time.
same way
And
as
I'm going to show
space?
why. I'm going to show. Yeah, I'm going to show.
But when we differentiate, we
Yeah, we got two. Yeah, we got two methods of differentiation.
both as
Yeah.
continuous.
No, we've got two methods of differentiation. We've got the method of limits, which is time, and we've got the method of infinitesimals, which is space. That's why we've got two methods of differentiation.
But they appear to be interchangeable. In other words, it appears that you're treating space and time in exactly the same way.
No, you're not. From differentiation, there's nothing to do with continuity or discreteness. What differentiation has to do with is variability. That's a different property. Variation is what differentiation is about, not discreteness or continuity. And we can do variation either as a discrete thing or as a continuous thing. I'm saying you can get real numbers both ways. There's two lots of real numbers, there's two lots of differentiation, and that goes through the whole of nature, this duality between continuity and discreteness. Let me just continue and then we can talk about that,
Sure.
because I'm not far from the end. Until we come to the next lecture, where we will suddenly see a mathematical structure that emerges once we have worked our way through this comparison of the three dualities, which I believe are the fundamental ones in nature.
So again, just so that I get into the right frame of mind, can I just say I can take everything you've done today as a postulate, as a supposition, so this looks to be reasonable,
Yeah.
and then see where it goes,
Yeah.
instead of trying to challenge every separate thing and understand every separate thing.
Yeah, I mean,
Because I just do not understand this question of continuity and...
no, it's a very difficult one.
Yeah.
That, as I say, I had to find new mathematics, which I didn't know about, to explain it myself. But I knew it must be true, because if it's not true, then we don't have exactness in the duality. And I think we have to have exactness in the duality at this level.
Something that then goes straight through my head as a result of what you've said. I once remember being made aware of essentially fractal mathematics as such. At the same time as I was facing the issue of trying to measure the short distance structure of something. And it seemed to me that two ideas sat in juxtaposition in a rather nice way. Would that be a fair statement? That fractal postulates in which you go in more and more and more detail, and you see even more and more detail with recurring patterns,
Yes.
as opposed to going into smaller and smaller reductionist type short distance phenomena, which you and I can live with very well because we believe in quantum physics, or we accept quantum physics.
Certainly accepted, yes.
But is that the difference?
There is a fractal aspect to this. There's certainly a fractal aspect to space in many ways, because that's...
That fractal approach seems never to define a limit to this.
Yeah, there's no limit to
Yes.
defining the divisibility of space. It is a kind of fractal approach. And of course, fractals are spatial objects in many ways. I mean, I think fractality is really the space-like type of thing, and chaos is really the time-like type of thing, as far as I understand. They're related, but they're not exactly the same thing. And there is a kind of fractal structure to space. You can keep dividing it and dividing it and dividing forever, and it will still look the same type of structure, whatever you do. And that's why it's discrete. It's not discrete in the same sense as charge. And I say that's because of the non-conservation. Because charge is a conserved quantity, so its discreteness is conserved. Whereas space is a non-conserved quantity, so its discreteness is still variable. But I think we will see what this is leading to in the next lecture. And I hope you find that particularly interesting, because I think that is probably the most important lecture after this one. The two are a pair. You can't do one without the other.
1 p.m.